This is A Geek Leader. Welcome to episode 140 of A Geek Leader podcast. I'm your host, John Rauda, and today's episode is brought to you by Private Internet Access. And if you haven't used Private Internet Access, then you're probably not surfing the web securely. I use Private Internet Access whenever I'm connecting from my home to do anything, whenever I travel especially. I remember a couple of years ago I went to a conference, and as soon as I connected to the hotel Wi-Fi, my endpoint protection was like pinging me that I was not secure, that I was getting attacked by different folks. So I immediately opened up Private Internet Access, connected to my VPN, and all that went away. Private Internet Access is an encryption service. It encrypts all your traffic going in and out. You can also choose different geolocations. So if I'm testing something, I make a change and my DNS servers are caching in my area, I can hop on over and log in California and then test it and say, oh, okay, DNS here, doesn't have the cache that I had before, so I can see the changes that I've made accurately, and it makes things so much easier and so much better. And you can try Private Internet Access for just $3 a month. Seriously, $3.33 a month is what it's starting at. You just visit ageekleader.com/VPN. Again, that's ageekleader.com/VPN. All right, Geek Leaders. Today on the show, we've got Paul Powers, the co-founder and CEO of Physna. He is also one of the Forbes 30 Under 30 winners, and he's a really smart dude. He went to Harvard, so give it up for Paul.
Thanks for having me.
Yeah, so tell us a little bit about kind of what your career has taken you and what you're doing now and how that kind of transpired, just to lay some context for the conversation.
Sure. Well, I only went to Harvard for about a semester, and then I actually switched to go to law school over in Germany. It's a long story how you go from astrophysics in the U.S. to law in Germany, but it's actually pretty simple when you think about it from when I explained the reasoning behind it. I kind of discovered that I didn't want to be I love science. I love technology. I'm a big geek, so this is the right show for me. But what I realized after a while was that, for me personally, I got more fulfillment out of the more macro picture of solutions, technology, science, et cetera. And I liked I like solving problems, but I realized that in the field of science that I was going into, you have to really follow the grant money, and you can't really choose a direction as freely as you might want to. So I decided to go into business instead. And I realized that, you don't really need any formal degree to go into business at all. So the question then becomes, well, why would you go to college for business? And I thought, well, you get it's sort of like boot camp, if you will. I mean, there's some things that it trains you to do. And I thought the real value in going to university before starting a business, that's again debatable if that's a wise move for everybody or not. But for me, I thought it would be really good to challenge myself and to get to know as much as possible about how the world works, the economy, how deals work nationally, try to see things from as macro of a picture as possible. And so I thought, if I want to do that in a big scale, I should probably go abroad and not stay in the U.S. I was homeschooled growing up. Long story, but I decided that it would be really good to just kind of spread out, and went over to Germany, learned the language, went to law school, passed the bar over there, and worked at a law firm for a while and learned a lot from it. I paid that off actually by starting companies. I started a company at the age of 16, and I've been running companies ever since. So for 14 years now, I've always been an owner of some company of some sort. And these have always been companies that pointed in, obviously, a technology direction. Sometimes they've been in the field of like business consulting, or they've been in the field of business-related services. Now what we do at Physna is we help bridge the gap between 2D and 3D. So we help give mechanical engineers and people who work with 3D models the same kind of tools that software engineers are used to using. So everyone listening, I'm sure, at least knows of GitHub if they don't use it every day. And that's something that just simply doesn't exist in the 3D world. It's really hard for mechanical engineers to do what software engineers do. And we only stumbled upon this because when I was in law school, I focused on intellectual property and realized that we could search any kind of violation of intellectual property rights imaginable except for three-dimensional ones. So if it was a song or it was a video or a picture or plagiarism, we could always find that. But as soon as it became a 3D model, it became impossible to find because there were these different types of models out there, and you'd be able to find parts inside of parts that have been manipulated and all this complicated stuff with all these different file types that don't really convert. So we decided to form a company to solve that. We explored the technology that was out there in the industry and realized that none of it was able to do what we wanted it to do. None of the quote-unquote geometric or shape search companies really did what we needed the software to do. So we ended up building up our own thing, and Physna is short for physical DNA. And what it does is it takes those 3D models and it codifies them and normalizes them into this proprietary, using proprietary algorithms and AI. And that process allows us to basically work with 3D the way that you would work with software.
So let me back you up just a little bit. Why did you pick Germany, of all places?
That's a great question. I don't even know that I necessarily have the perfect answer. So I skipped a step in there just for the sake of brevity. I did an exchange year in Switzerland, kind of when I was trying to make my decision if I wanted to stay in science or so after Harvard, exchange year in Switzerland, thought through it and decided on business. And I learned the language there. Well, I learned Swiss German, which isn't really the same, but it's close enough. I could understand German well enough. And so I applied kind of for fun over there, thinking it might, that I probably didn't have the best chances because Heidelberg is the university I went to, and that's a very elite school. It's very hard to get in. It's also very hard to get out. The tests are very difficult, and a lot of people fail out, even Germans, and the language barrier is immense. So I thought the likelihood of actually getting accepted was fairly low. But when I got accepted, then I thought, well, maybe this is fate. I didn't know at the time how hard it was going to be. I didn't realize, I knew law school in a foreign language was going to be difficult, but Germany especially, turns out, was immensely hard. They have one of the most rigorous law programs in the world. It's really tough. And if I could go back and do anything different, I might have chosen to do it in Switzerland or in Austria, or maybe just go to England and do it in English, perhaps. But it ended up working out, so I can't complain too much. But it was hard.
Yeah, I did an international business course, and where we spent 2 weeks in Germany and in Austria, and it was pretty awesome. We toured the University of Heidelberg actually, which is pretty interesting.
Awesome.
Yeah, small world. But I love Germany. It was great. It was a great experience. It was definitely different for sure, coming from America, and not even that, the South of America,
yeah.
And getting up there and trying to learn the different cultures. It was fascinating for sure.
Yeah, it's a really different place, and it's kind of, I was there from the age of about I went over. So I was at Harvard at 16. I went from there. I went right over to the exchange year. So if you count that, it would have been the age of 16 to the age of 26, so 10 years. That I spent over there, and those are very transformative years. So I kind of feel like I went through two culture shocks, going over there and coming back.
Yeah, I bet so. Yeah, wow. So, when you got into the space of, I guess we'll call it, you were trying to figure out a way to, was it to protect the intellectual properties of the 3D models that were being created, or was it just an integrity thing? What was the actual driving force that said, hey, this could be a business?
Well, trillions of dollars are lost every year to patent infringement, right? And we don't really have a preventative way of stopping someone from infringing on patents. We just have a reactive way of handling it, where you sue somebody after the fact. But that doesn't really work. It's getting increasingly expensive, and it's easier and easier to infringe upon physical patents with things like 3D printing and the democratization of a lot of those tools. Even if you don't have a 3D printer, it's a lot easier to get a prototype made now than it was 10, 15 years ago, and increasingly so. And as a result of that, plus 3D scanning technology, it's increasingly easy to copy 3D goods. And that means that the return on investment that you get from your R&D, if you're the company whose intellectual property is being stolen, is, increasing, it's diminishing. And the odds of you being ripped off are increasingly high. So, you're not going to, if someone is, let's put it this way, it's worth it to sue somebody if the damages that they're causing you are hundreds of millions of dollars a year by, making fakes or something or knocking off your product. But it's not worth it to go sue somebody who made one 3D printed or machine shopped version of what you have, and that's only worth $20. I mean, if hundreds or thousands of people are doing that around the world, you can't sue all of them. It's just too expensive. So the idea was, let's do two things. Let's, one, prevent intellectual property theft, but three, let's give people an avenue to actually take advantage of that new technology. We don't want to get in the way of technology. What we want to do is, obviously there's a shift in how supply chains work, how manufacturing works in general. So what we need to do is embrace that and say, why don't, so we wanted to monetize that process and say, instead of just stopping people, give people an option. This is something that we wanted to give companies an option to do, of having the right to manufacture your intellectual property. So maybe, let's say you're Nike and somebody wants to produce your shoes. A stupid example, but let's roll with it. Let's say that the profit you would normally make off of a pair of shoes after all the distribution costs and shipping costs and everything, let's say you'd make $20 in profit. Mm-hmm. If somebody is willing to pay you $30 for the right to manufacture that shoe, that's better for you, right? Than even having made the shoe yourself. So that was kind of the concept behind it. Now, what we focus on today isn't really purely intellectual property protection. Actually, we've a majority of Physna users use it for engineering, for productivity, right? Just so they're not redesigning something from scratch. They're able to reuse the models they have, find similar models, reduce procurement costs, reduce inventory, just by understanding, like, this model is in all these models, and you have this many duplicates in your system, and you have these options as components for this thing, not just this one. Everything in 3D is listed by a part number, and those part numbers are typically, there's typically many part numbers for the same thing in most companies that we find. And so it's just the waste is incredible. Physical engineers, so mechanical engineers, would be 5 times more productive if they had the same tools, basic tools, as software developers. Things like the ability to search with 3D, the ability to having autofill, having predictions, being able to do comparisons in a very quick and effective way would make them 5 times more productive than they are today. That's a big deal. But then what I didn't mention is that the fact that they're not productive today is in large part because they're recreating things they don't need to. That actually has a lot of cost down the road. So it has cost in the supply chain because you have all these duplicates. All these duplicates mean that you're not realizing that you're ordering all these different part numbers and small quantities throughout the company instead of ordering one big order in bulk. And you're not competing the bids. You're not looking for competitive bids for this giant order. You think that you can only order this one part number from this one supplier or this other supplier. So there's no competition, so the prices go up. And it amounts to about 40% on average of supply, the cost of procurement. About 40% of that is waste. It's would be reduced by 40%, let's put it that way, if people had that kind of an insight. And then the same is true when you get into spare parts inventory. If you have a machine or some kind of fleet of vehicles or something, you have to have a certain number of spares for every type of part. Well, if you have 5,000 components on something and you think that there are 5,000 different parts, now you have to get 5,000 spares. When in reality, if you realize that they're all the same thing, maybe you don't need to have one-on-one. You don't need to have 5,000 of them, right? So that's a big part of what Physna is today. And then we're also creating a really big universal library of parts that integrates in with PLM and CAD. So there's a lot going on in that space. And then one other area I haven't mentioned, this is a smaller component of what we do, but the technology that we have allows for the protection of assets from cyber attack, right? Or at least the detection of attacks that have taken place. And we can go more in depth in that if you're interested.
Yeah, I definitely want to talk about cyber attacks. But before we get into that, one of the things you're talking about was reuse of parts. And we recently got a Tesla Model X probably several months ago, and absolutely love the car. I'm a huge Tesla fan now because I have it. But one of the things I noticed about it, I don't know if you've ever driven a Tesla. Have you?
No.
Oh, you really should. It's a game changer for me anyway. But I noticed that the parts are so interchangeable between different pieces, and it's almost like they took the approach. Like I have an F-150, and I also love my F-150. But depending on what type of F-150 you have, do you have a Super Crew? Do you have a two-door? Do you have extended cab? the parts are going to change. Like even parts that look the same, like the connectors for the headlights, there's going to be something slightly different about them. Whereas, there's parts you can buy for the Model X that are the exact same as the Model S. They just reuse the same parts. And much of the interior is completely reused. And I've noticed that, when I'm looking for, aftermarket parts, it's like this fits the Model S and all Model S's and all Model X's. Like, oh, well, how is that possible? Well, it's because they use something to figure out that they can reuse these parts for multiple different models, whereas I didn't see that happening in my truck or some more legacy vehicles. And I'm guessing they use something similar to what you guys are doing.
I can't speak for Tesla. I don't know what they're using. But what you're talking about is actually standardization of parts. Part reuse is, I'm talking about the models themselves. So when you design something new, you're not starting from scratch, or that you're not redesigning something you've already designed. It's absolutely a smart business tactic to standardize as much as possible, both for your own production costs, but also for the sake of your customers, so that they do have interchangeable parts. So that's a wise business tactic. Now, there is an aspect of our software that helps with that, which is, sometimes what you'll find is that many different people have designed many. So in the case of your F-150 or whatever, right, there are all these different components that, depending on which model you have, they're not identical. And so what that means is, to me, is that most likely what happened was somebody at Ford, when they were designing that car, they were probably in different departments, and they probably designed things a little bit differently for the same application, which means, that was a duplicate. Those are kind of duplicates, and they could have reused that. But also, if I were to look back now, let's say if you were at Ford and you were looking at what to standardize, now you'd have the dilemma of, okay, we have, let's say, 5 different parts from these 5 different trucks. We have to choose which one we're going to use moving forward. So the question then becomes, which one is the best, right? Which one performs the best? Which one works the best? Which one fits the best, et cetera? And so Physna has some functionality that allows you to make those predictions. So one of those is that is a geometric fit analysis, right, where it'll look at different options for a part, and it'll say, this is going to work the best geometrically and functionally. This is the best part for this, for this mating bit over here. And the second thing that we do is, and this to me is one of the coolest things about what we've uncovered here, is that machine learning is, I think, one of the coolest things in the world. And I really do think that in the case of machine learning, the hype is for a good reason. Not all technology can say that, but I definitely think that's true for machine learning. And what we've noticed with 3D models is that, in the past, almost nobody, when they talk about machine learning in the world of 3D, is being genuine when they say that. Typically, when you hear people talk about AI or machine learning in the context of 3D, they're kind of stretching the definition of that a bit. And the reason is that these different file formats, when you don't have a common ground, when you don't have a normalized structure, it's really easy for the models to get confused, for the machine learning to get confused on what to interpret from the different models, because you're basically not using a harmonious data set. You're using 40 different data sets, and without knowing how to compare the different ones. So true machine learning, you require some degree of regularity in the data. And so with Physna, we've integrated with machine learning, and that's enabled us to make predictions very, very quickly about how parts will perform, how parts will, what the cost will be over time, when they might break, how hard or easy they might be to machine, what the options are to have this supplied to you, how it can be manufactured. I mean, all of this without really much data at all. We just, once we see the part, the AI or the machine learning, we're making these predictions on the fly. And what's really exciting about it is that when you get into the world of 3D, machine learning actually takes on it is a quantum leap there. If a good analogy would be, if I take your picture and I try to apply machine learning to that picture, I need a lot of pictures of you before I can make any predictions, right? I need a lot, tons of pictures of you before I can start making predictions. But if I were to take all of you, right? I mean, there's a lot more data in you. You are more data than a picture, a lot more, right?
I hope so.
That's the difference between 2D and 3D, right? I can only see one perspective of you. I can't see inside. I can't see the back. Can't see the other perspectives. But in 3D, I see much, much more, several orders of magnitude more. It's actually like a 10,000 or 100,000 to 1 ratio. So when you get into 3D, the kinds of predictions that you can make, especially with AutoML and DNN and TensorFlow and some of these newer tools out there, you're able to make some predictions that are just mind-boggling. I mean, with a very small data set, you're able to make predictions that are crazy. We had a customer who came to us, and they make consumer goods. And they had they weren't interested in finding parts because they don't make that many new parts. they were interested in analyzing which of their different designs and mock-ups would perform best in the field. And they were noticing that over time, the small geometric changes that they were making to these models were causing them to either not be manufactured correctly or break, or they would break in shipping, or they would just not perform as well in the long run. And they couldn't figure out the causality. This company has many thousands of engineers, and over years, they've not been able to figure out why. So we took a sampling of those models and we said, give us 5 bad ones and 5 good ones. 5 models that turned out well the way you want them to, and 5 that didn't. And we were able to predict with over 99% certainty after just 10 models total, which of the following models after that would come out correctly or with a problem. Machine learning is an amazing asset there.
Well, I would imagine like with each example, you're getting, thousands, if not millions of data points that the machine learning could probably analyze and figure out. And, it's going to be far better, I guess, than just one picture like you talked about with, an individual.
Right.
Yeah. So when you guys went down the machine learning aspect of developing your software, what was the initial hopes? Is it what you guys got, or was it kind of like, well, we don't know if this is going to work out, we'll give it a try, or, I'm still curious. I'm a novice when it comes to AI and machine learning in general. So any feedback you can have for some dummy like me would be helpful.
Oh, well, I'm CEO, not CTO, so I can only go so deep myself. But the reason we actually started the machine learning part, so we've had some degree of machine learning and AI in the software kind of all along, but we've really focused on it and made it a big part of the software over the past year. And the thought that went behind that was we actually it was not really an aha moment. It was really just that customers were coming to us asking for us to figure out certain bits of data for them. And we realized that if we were to do all of that algorithmically, we'd have to basically make all these custom versions of software because they're insanely specific to these different companies. And we thought, well, how are we going to do that? We don't want to become a custom dev shop, where we're redoing our software for every single company. So we started exploring AI, and we thought, look, if we can make predictions based on the data that they already have, which is custom to them, they know what they are tracking, they know what they want to track, they know, all that data is already there. If we can just take their existing data and make predictions, we'll let the machine learning figure out what to look for and how to look for it. And if it works this quickly, it's not really worth it to do a custom algorithm. The thing about algorithms is that yes, they work perfectly on day one for what you program them to do, but very rarely do you actually know everything you want it to do. And we've seen that machine learning is actually, after a little while, and not long at all in the case of 3D models, is much more reliable than algorithms. Like I said, in that case where that manufacturer wanted to figure out what was going on with those different models that they had and why some were good and some were bad, it would have been extremely complicated to figure that out algorithmically, which is why they haven't been able to do it. Machine learning, by letting it basically unsupervised machine learning, basically saying, some degree of unsupervised, some degree of supervised, it's complicated, but there's different degrees, different tactics that we use. And basically what it does is it figures out what it needs to look for. It kind of says, okay, well, these are good, these are bad. Let me figure out why. We don't have to write a script saying, check out if it's this, see if it's this, see if this is causing it. It just looks at everything. And then it figures out causality on its own. And then it says, okay, from now on, we're going to look for these traits, and that's how we're going to predict good versus bad. So it's amazingly powerful. I mean, we really, basically, we started doing it because we realized that the applications were more numerous than we had people to develop.
Yeah. So do you think most of these discoveries that were found through the machine learning were more like pattern recognition type discoveries that just humans aren't good at, or was it deeper than that?
That's a great question. The weird thing about machine learning is that sometimes you don't know why.
Yeah, I know.
The answer is what it is. You can kind of trace it back, but it's complicated. So in some cases, it's very easy to tell why it's making certain predictions, right? Because let's say for a human to tell, you can look at it and say, it thinks that this thing is used for hardware assembly that's for plumbing, and it's probably made out of brass. It's probably going to cost this much. And if you look at it, you're like, yeah, I can see that. It looks to me like this is a brass pipe, and it looks to me like it would probably cost about that. I mean, you can kind of follow the logic there. In other cases, it'll make predictions that I'm not going to say are illogical. They're not, but they're ones that you wouldn't necessarily automatically make. Like this one is going to not perform very well if you make it with this machine. You need a lot of. It's not that you wouldn't understand why if you had all the data. It's just that we often don't have all the data. We don't know exactly off the top of our heads. Why is that combination of this design with that manufacturing process going to cause a problem? And so if you were able to just dive deeply into that data set, sure, you'd always be able to figure it out. It's always something that's comprehensible in some degree, but just typically the reason that it doesn't always pop out, and the reason why machine learning is so valuable is that, first of all, it's doing the work for you, and secondly, it's making predictions that are beyond what humans are capable of because it doesn't rely on tribal knowledge. It relies on large data sets that for humans are just almost an incomprehensible amount of data.
Right. Yeah, I think it's super fascinating. I've had we had the CIO for a hospital system. They were talking about how they're using AI to kind of figure out some of the scans of people, and it can detect like cancer significantly better than a human can. And it was a lot of times it was things that humans weren't taught to look for, but the machine would realize, hey, from all of our samples, we realize that this is an indicator of cancer that you guys aren't aware of, and so we're using that as our indicator.
Exactly, and we've actually had a lot of talks with people about that, and one of the things that I've heard, and I am not claiming this because this is conjecture, right? But a couple of health organizations have approached us saying that they feel very strongly that based on how Physna works, there's a good chance that we'd be able to pick up cancer cells at almost down at the cellular level much earlier than two-dimensional analysis would be able to pick it up or anything else, and that the AI would be able to figure out causalities that, again, like you said, we're not trained to look for, or we have a hard time picking up with the way that data is displayed. One thing that a lot of people overlook is that there's a lot more data than we actually see. So one of the things about CAD models, for example, or any of the things that you look at if you're a doctor at a hospital or you're a mechanical engineer, your computer can only display so much data and so much accuracy, right? So it's built to kind of show you a generalized view of what something looks like. And even the human eye is not meant to pick up literally everything, right? It's just meant to pick up what matters most, your reflected light. And your computer is almost like a step below that, where it's trying to pixelate data to you in a way that represents what it might look like in real life. So that representation is not a complete representation, and that normally doesn't matter, which is why no one really cares normally, right? Normally you don't care if there's some microscopic thing that's off a little bit in a 3D viewer, because you just can't see it and you don't pick it up and you don't notice and you don't really care because the data is what it is. But when you get into areas like cancer research or quality control or cybersecurity and those types of areas, you really do have to know, data at a much lower level, because any little thing can end up causing a big problem.
Yeah, absolutely. And correct me if I'm wrong on this, but I think because of some of these discoveries, you guys sort of stumbled into working with cybersecurity. Is that correct?
Yeah, what we found, so the word cybersecurity is almost a little bit misleading. The reason we say the word cybersecurity on our website is because if we go into exactly what it actually is, no one would understand it, what we were saying, because it doesn't make sense. I mean, truly what you're doing is it's digital, it's like three-dimensional digital data and integrity validation after a cyber attack takes place, which if I said that, no one would ever click on that link. So we just say cybersecurity and people kind of get the gist. What we're doing isn't actually protecting the model, right? So we're not actively preventing someone from attacking your company. What we're doing is, assuming that you have some degree of cybersecurity, you can always hack just about anything, unfortunately, right? You can hack into things. Now, Physna is extremely robust and has a lot of security measures. And I would say we're as hard to hack into as just about anything else you're going to find out there. But let's imagine that your company's hacked, not with or without Physna, right? Your company's hacked and someone has access to internal data that you have. The danger in 3D is that it's harder to see if someone manipulated that data than it is in 2D, right? In 2D, I can tell if someone manipulated my data because I see that my emails say different things than they said yesterday, or, the numbers changed on a spreadsheet. That's something that you can kind of quickly pick up on. But in 3D, what can happen is they can make manipulations to those 3D models that you cannot pick up on because the viewer cannot present those changes. So you'll look at a model to make sure that nothing changed on it. There won't be any revision history on it. There will be nothing indicating something changed. But and actually, this is a really easy hack to do. Unfortunately, this is something you could show someone how to do in 30 minutes who doesn't even know how to hack a computer. They could learn it in 30 minutes. It's really easy, even if you don't know CAD. It's really simple to do this. Unfortunately, you can get the certain data inserted into or manipulated in a 3D model that won't show up in the viewer, and there's no way you can tell that it was manipulated, but it did happen, right? And so when that model then later on, after so many, it gets handed off and goes through whatever processes, when it gets manufactured, that model is now compromised. But quality control says it's perfect because, hey, look, this is exactly what you guys designed, right? I mean, you said to design this, and I built it to spec, so it's perfect. And then that model gets manufactured and it's put on a plane or it's put on something else, and if that data is compromised, you actually do have a physical change, and those changes are very real changes. And a lot of people make the mistake of thinking they're always microscopic. They can be, but they can also be much more significant, and they can just be hard for the human eye to pick up on, or they could be inside of something. They can be the way something is aligned with something else, and it can be really, really hard to detect. And typically, those types of manipulations lead to cases where those parts are compromised under stress. Those parts, because if it was a huge, obvious manipulation, it would have showed up on the viewer. It would have been something that you would have picked up on just by manufacturing it. Hey, there's a big hole in the middle of this thing, or something. But if it's less obvious than that, typically it's under stress. So where you really have to worry is when you're developing something that is holding, transporting, or dealing with critical data. So if it's a medical device, if it's if you're in automotive, if you're in aerospace, any of those areas especially, you really have to be careful about the integrity of your models. And what I'd be very worried about is, let's say that you are, let's use Boeing as an example, right? Just because I know because they're a big aircraft manufacturer. If Boeing found out that they were hacked, right? Someone had managed to get into their system. It would be, if they don't have a way to validate that nothing happened to their 3D models, then you basically have to make one of two very hard decisions. Either one, you have to say we have to assume that they were manipulated, in which case Boeing doesn't exist anymore because you're not able to manufacture anything anymore. Your models are all gone, right? And you have to basically reverse engineer them from existing parts, which is enormously and impossibly expensive. Or you can say, we're just going to assume that everything's fine because we can't see the changes with our eyes, which is an enormous risk to take because your planes might start falling out of the sky at some point, right?
Yeah.
So that's what Physna does, is it finds out if a manipulation took place to that model. And we basically compare that, the codified data of the model after a hack to the codified version of that data from before the hack. And we can pick up on any type of change whatsoever. So if anything was modified in a way that would actually change what comes out of manufacturing in any way, shape, or form, that literally has to show up in Physna. There's no way it will not show up in Physna because we rely on that data for that code.
That seems like it's such a huge deal. I know this is probably I don't know if it was this past Block Hat or the one before, but they did a demo where they showed how insecure, you mentioned healthcare, how insecure some of the scans and stuff are and machines at healthcare, where they had hacked a few of them just to show you that they could, inadvertently add in elements to a scan as it was going on to show that, so the rad tech person would see cancer on a patient that did not have cancer. And they were saying that, the implications of this is that we could do this for a presidential candidate, and then it will come out that this person has cancer and they could lose the election because of this. And it's kind of one of those things that you could, very easily go in there and manipulate something. But I mean, how much more could it be if we did that to airplane manufacturers?
You're right. And what's really scary about all of this is that, we're talking about the number one threat in cybersecurity. What I'm referring to is what I think you might refer to as a cyberphysical attack, right? It's not just attacking your banking data. It's attacking the physical integrity of something. And not just one thing, of everything that ever gets manufactured in the future. Oh, wow. And that's really dangerous. And it's an area where most people are either A, unaware of the threat, like completely unaware that that's possible and that's as big of a threat as it is and as easy as it is to do, or B, they just haven't made the investments. I mean, the biggest target of cybersecurity in general, or cyber attacks in general, would be manufacturing and then the industrial world. It's just way behind, in terms of how much cyber security they have and the protection mechanisms they have, but more importantly, the not just protection, but detection. You're never going to keep everybody out of your system forever. Eventually, someone will penetrate it in one way or another. What is important is not, keeping people out. It's what happens after they get in. Do you know what they did? Are you able to recover? Are you able to rely on your data again and know that the integrity is still there? And if not, then no amount of security in the world is going to preserve your business, because eventually it'll happen.
Yeah, so I take it back to the automotive industry. If you think about if they're checking in their models, is that what you call it? Checking in, kind of like with GitHub, iterations of changes that may go on with 3D modeling.
Everyone has different. We can go down a big rabbit hole on that. And typically, you would save it in like a PLM or a PDM system, which is kind of like what CAD engineers would use as kind of like their repository. And then Physna kind of acts like, I guess you could almost say like a little bit of I don't know if GitHub's the right word or not, but it's very similar to, it can act to a very similar thing to that. Yeah, we sync up with our PLM data, so we know if something gets changed, we see the change happen.
You see the change, you kind of can go back to when this change happened.
Right.
So if someone, if let's say there was an auto recall and it came out and they don't know how to test, hey, what caused this issue? It wasn't happening to models we built before this one, but it is afterwards. Did something happen to this design? You guys could go in and check that and figure all that out.
Yeah, we wouldn't have to go in at all. The user of the software would have a really easy time doing it. They would basically just ask the software to compare all the models between the two cars, that are supposed to be the same, right? Mm-hmm. Or it could look at the AI predictions and see if that was something that could have been predicted. But importantly, they can look at the differences between these models, and if there's any tiny difference between them, Physna will pick up on it.
Yeah, awesome. Man, that's super fascinating. I want to get back to one more thing about, I guess, the technology that you guys are doing. As you're, kind of leading this company, and how is it that you make sure you hire the right people to kind of do something that's really never been done before, right? This is kind of a cutting edge technology. How do you go out and find the people that you think would be a good fit for your team, and what are some of the criteria that you're looking for whenever you're looking for a tech leader?
We are always looking for technologists at Physna, like literally all year round.
Hey, we're on the right show to find some.
There you go. Yeah, everybody, if you're interested in applying, please, please do. We are always constantly looking for talented people here. It's really hard because we get a lot of applicants that are very motivated to work in this space. And what we look for is we look for experience. We look for people who've worked on challenging new projects in the past and worked on problems that were as unsolved as can be. Because what we're working on, there's no roadmap, or that's the wrong word, I guess you can say. That there's no guideline in the industry for how to build a Physna, right? Because it's not a thing that's defined by. There's no company I can think of that's really close to what we do. There are some that are analogous, but they're not ones that are similar, I guess, if that makes sense. And because of that, and because the technology is so different, and we're doing something that's never really been done before, we can't really rely on past experiences of other companies. We can't really rely on people who worked at this company or that company. But we have to look for people who just are really, really, really smart and can figure things out. So what we look for is a combination of experience with building new and exciting and difficult and complicated projects at large scale, especially. And some degree of startup experience is normally helpful. We look for people who have a wide variety, or at least a really good understanding of code in general, more like a full stack person, than anything else. And then we look for people who, so after we have a feeling that they've done well in the past on everything else, then we look for how ready they are and willing they are to learn how to tackle a new problem. And what turns us off is when we find somebody who is either assuming that they've got some degree of experience and everything else checks out, if they are too stubborn, or too single-minded and they're closed-minded, I guess you should say, about how to go about coding something. And they say, well, it has to be done this way. There's no other way to do it. that scares us, right? Because it makes us think, well, that's never proven to be true. There's never just one way to do something. Okay. There are lots of ways to do it, and what we need to do is be open-minded to, is this the right way to go about it? Is there a different way? And big rule that we have at Physna is that we're just very transparent and open about what works, what doesn't work, what we need to fix, we fix it, and no one is allowed to get we don't like it when people get emotional about it. If you build something and it's broken, we'll fix it, and that should just be a learning experience. So we want people who have, a lot of drive, who can see the future, they can see into the future, but they're future oriented, they're new tech oriented, they think outside the box, and they constantly learn. We want people who are constantly learning.
Yeah, that's awesome. On my team, I have a little code of things that we are, and one of the things I say is we're not experts. We'll always keep a posture of a student, always learning, because
right.
it's I think that's the mindset you need to have, is always looking for abilities to learn and grow. Because once you think that you've gotten it all and you figured it out and this is the one way to do it, you realize that you're wrong.
I typically tell people who apply, as far people who are applicants for a developer or something, that if you haven't read up on new updates and software methodologies and technology or whatever for in the past month, or maximum in the past 3 months, then you're probably expired almost, because things happen so fast. You have to, just to keep your level of expertise, you have to stay on it. And if you don't keep up with what's going on in the world and the newer types of code methodologies and tools that are out there in the market, you will very quickly be out of date. Essentially, you won't be working with the latest and greatest, and no amount of experience will make up for that in the long run. So that's a very important thing. I think you're very wise to make that mantra in your company.
Yeah, that's one of the things. I also teach part-time at Winthrop University, and I tell my students in computer science, that the jobs that you'll be getting when you get out of here don't exist today, and the things that I'm teaching you will not be relevant by the time you graduate. Which is sometimes hard to say as a teacher, but it's the truth.
Yeah, I have to be very honest. We don't really care about academic background too much when it comes to these applicants. What we care about is experience more than anything else. We've literally turned down PhDs from Ivy League universities and all kinds of things in favor of people who dropped out of high school. All we care about is results. What can this person actually do with code? How much they know about how code used to work, essentially, or how much other types of study they've done isn't necessarily going to matter a bunch. It's really rare for it to come down to educational background at our company. Yeah.
Well, I appreciate having you on the show. It's been a lot of fun. I feel like I've learned a lot about the things that you guys are doing, and maybe some of the threats that I didn't know existed. Do you have any advice or anything you want to leave the audience with, or tell the audience about how to connect with you or learn more about Physna?
Yeah, so Physna is spelled Physna, or physical DNA. A lot of people think it's Physna. It's not. It's Physna. And you can reach out to us over our website, physna.com. You can find me on LinkedIn, Paul Powers. I'm always happy to chat with people. I'm always looking for applicants. We're always looking for people who are interested in getting involved in one way or another. I'm always happy to talk to somebody if they want to learn more. And my advice in general would just be, question everything around you and be open, be open-minded to a different world, and realize that somebody is going to have, like you said to your students, the world is going to be so different in a few years that everything we're talking about today is not going to matter. And at one point, someone in 5 years from now will listen to this podcast, and hopefully Physna will be doing amazing by then, right? But what we're talking about today in 5 to 10 years probably won't be considered, cutting edge anymore. The cutting edge will be somewhere far away from where it is today. So,
yeah, that's great advice. All right, well, thanks for coming on the show. I really appreciate it, and have a Merry Christmas.
Thanks for having me, and you too.
Hope you guys enjoyed that episode with Paul, and if so, please leave a rating and review in iTunes. I'd greatly appreciate it. I think it's called Apple Podcasts now. But also share this episode with a friend. Share it on Twitter, LinkedIn, or face-to-face with anybody you come in contact with. We want to get more listeners to A Geek Leader, so please do that. Also, you can visit the show and see show notes at ageekleader.com. And don't forget about the discount on private internet access for all your secure web sharing and web viewing and web searching and everything else that you do on the web at ageekleader.com/VPN.